After completing the stability calculations, I further advanced the aircraft's propulsion system analysis using OpenVSP. Compared to traditional CFD systems, OpenVSP offers a modular modeling approach and connects with Python in a very fast and efficient way. In OpenVSP, the aircraft is modeled while retaining the configuration information from previous calculations. The structures and weights of the pilot, electric motor, landing gear, augmentation devices, and battery are also represented. This more complete model is then subjected to aerodynamic and stability validation, serving as a double check after switching modeling environments. By comparing the full aircraft results simulated in OpenVSP with those from XFLR5, it can be seen that the values of CL, CD, CM, and stability remain essentially the same. After defining the overall aircraft model, it is necessary to determine the propulsion core, the propeller. The size, number of blades, and degree of twist directly affect the power delivery capability. In the video Conversion électrique des petits avions, I confirm the use of Pipistrel's electric motor and its dedicated battery, with a specified maximum rotational speed of 2,500 revolutions per minute. I will use this standard as a reference to evaluate whether the aircraft can meet the takeoff performance requirements. As a test calculation, I initially selected the propeller parameters based on experience and adjusted them iteratively to meet normal takeoff requirements. If specific takeoff requirements are defined, such as ground roll distance, V1, or VR timing, the propeller parameters can be derived in reverse from these targets. OpenVSP provides an automated standard propeller model that can be used directly. It allows calculating the thrust performance at a given rotational speed, and then the propeller can be modified to achieve the desired thrust effect. The adjustable parameters include basic geometry, such as the number of blades, radius, hub size, and rotation direction, as well as detailed features like blade airfoil sections, thickness, twist angles, span-wise chord lengths, and pitch distribution. However, in my opinion, if more refined thrust calculations are needed, tools like ANSYS Fluent or Star CCM Plus should be used for simulation. With the adjusted propeller parameters, the calculation shows that the stable thrust at maximum rotational speed is around 2,050 newtons. The takeoff thrust must overcome three main components: the friction drag of the airflow, the parasitic drag, and the induced drag. With OpenVSP, it is also possible to calculate the average CL and CD0 of the full aircraft model. According to the stall speed optimization performed earlier, CL during takeoff must be greater than 0.85. Here, the average CL is around 0.89, providing a certain safety margin. Using VR speed as a reference, the result for CD0 can be obtained. The largest contributions come from the main wing and the fuselage, with the sum of all components giving a CD0 of about 0.02404. With the takeoff equilibrium equation as a reference, all the parameters are now defined and can be used in the takeoff performance calculation. The simplified takeoff model is treated as a two-dimensional motion with variable acceleration. During the increase in speed, lift, drag, and friction forces are constantly changing, so an iterative approach is applied for the calculation. I used both the Euler method and the Runge-Kutta method as a double validation to compare the results. One point to clarify is that I do not know the exact acceleration profile of the E811 electric motor. Therefore, in my simulation, I assume that the propeller has already reached its maximum rotational speed before the aircraft releases the brakes. This means the initial velocity is 0, and the initial thrust is about 2,050 newtons, corresponding to the stable thrust at maximum RPM. For the ground friction coefficient, I used 0.02, representative of a concrete asphalt runway. The Oswald efficiency factor generally ranges from 0.6 to 0.9. Considering my aspect ratio of 7.6, I selected 0.8. The results show that the aircraft's takeoff time is about 9.45 seconds and a takeoff distance of around 150 meters. For small or ultralight aircraft, the results are generally consistent with expectations. If needed, the performance can be further refined by modifying the propeller configuration or adjusting the aircraft layout to change the aerodynamic forces. With the propulsion system now installed, the next video will focus on calculating the aircraft's performance across different flight conditions. Thank you again for watching. If you are interested in the L'Avion Ideal channel or would like to follow the guidance from Lion, don't hesitate to subscribe.